Welcome to the third and final lesson in the electrode potentials topic from the OCR syllabus. Today we'll be looking at an emerging application of electrode potentials, which is fuel cells. The learning intentions for this lesson are to apply the principles we have learnt about electrode potentials to modern storage cells, to explain that a fuel cell uses the energy from the reaction of a fuel with oxygen to create a voltage. We need to describe the changes that take place at each electrode in a hydrogen-oxygen fuel cell, and the final intentions involve recalling the advantages of fuel cell vehicles over more traditional vehicles, how in practice the hydrogen may be stored, and possible limitations of hydrogen fuel cells. So to begin, a fuel cell converts energy from a reaction of a fuel with oxygen into a voltage. The fuel can be hydrogen, but many other hydrogen-rich substances are being considered, for example methanol or methanoic acid. The overall reaction that occurs in the cell is that of a complete combustion reaction with oxygen. In a hydrogen fuel cell, the overall reaction is 2 hydrogen plus 1 oxygen molecule reacts to form 2 water molecules, according to the equation shown on the slide. In an acidic hydrogen-oxygen fuel cell, at the positive electrode, oxygen is reduced to form water according to the equation oxygen plus 4 protons plus 4 electrons reacts to form 2 waters. This half cell has a standard electrode potential of 1.23 volts. At the negative electrode, hydrogen is oxidised to form hydrogen ions according to the equation hydrogen reacts to form 2 protons plus 2 electrons. This is the standard electrode potential and so has a standard cell potential of 0 volts. If we were presented this question in a similar way to last lesson, both half equations would be reductions, as shown on this slide. So the hydrogen half equation is more negative as hydrogen is a better reducing agent than oxygen, and so it is this one that we flip over, giving us the overall combustion equation once the hydrogen ions and electrons are cancelled out. Adding the standard electrode potentials together, the cell generates a voltage of 1.23 volts. There is also an alkaline hydrogen-oxygen fuel cell. Use the half equations and cell potentials on this slide to have a go at writing the overall equation for the reaction that occurs and calculate the cell potential. You can pause the video now. If you've done this correctly, you should notice that the overall equation is the same and the cell potential is also the same. So it doesn't matter whether it is an acidic or alkaline fuel cell. You don't need to know all of the equations, but you do need to know the overall equation in all fuel cells is the complete combustion reaction with oxygen. Scientists are developing other fuel cells with hydrogen-rich fuels like methanol. Reasons for this we will look at later on in the lesson. Typical questions will ask you to determine the oxidation and reduction reactions that occur in these fuel cells. Let's have a look at how we would go about this. You will usually be provided with one of the half equations. The one on the slide is the one you should be familiar with, which is the reduction of oxygen to water under acidic conditions. We have learnt that the overall equation is the complete combustion of the other reactant, in this case methanol. So let's write the overall equation for the combustion of methanol. In order to determine what reaction occurs at the negative electrode, we need to compare the half equation we have with the overall equation. Methanol must be on the left-hand side as a reactant, and carbon dioxide must be a product. If we remember back to writing half equations, we are allowed to add water molecules and hydrogen and hydroxide ions. We can ignore the hydroxide ions as this reaction is under acidic conditions. Therefore, in order to add an oxygen to the left-hand side, we add a water molecule. The methanol will react with the water to form carbon dioxide. If you need a reminder on how to write these half equations, you need to go and watch the first transition metals video. So continuing, There are now 6 hydrogens on the left-hand side, so we need to add 6 hydrogen ions onto the right-hand side. We are now balanced with the exception of the electrons. We know it's an oxidation as oxygen is being reduced. So electrons are on the right and the charges on both sides need to balance, so it must be 6 electrons, as there are 6 positive hydrogen ions and no charge on the left-hand side. So we have now deduced the other half equation. To double check, we just need to combine both half equations to make sure we end up with the overall combustion equation, which we do. To get the electrons to balance and cancel, we must multiply one equation by 3 and the other by 2. Now that was quite complicated, so let's try a further example to ensure you're happy. This time you're going to try and deduce the half equation that occurs with ethanol. On this slide is the reaction that occurs at the positive electrode with oxygen. You firstly need to write the equation for the complete combustion of ethanol, then using your answer to part A and the half equation on this slide, deduce the equation for the oxidation of ethanol at the negative electrode. Pause the video now whilst you try and work it out. So here's the answer. The overall equation for the combustion of ethanol is shown. Ethanol must react to form carbon dioxide. Now to balance. 2 carbons on each side. Adding up the oxygens on the right hand side comes to 4. There's already one oxygen in the ethanol, so only 3 water molecules are needed on the left. There's now a total of 12 hydrogens on the left, so 12 hydrogen ions need to go on the right. I'm balancing the charges with electrons, so there are 12 on the right. Double checking by combining the 2 half equations and ensuring it's the same as the overall equation, we need to multiply the oxygen half equation by 3 and cancel out the 3 waters, all of the protons and all of the electrons. If you'd like to try a further example, try to deduce the half reaction that occurs in the alkaline fuel cell with methanol as the fuel. The reduction of water under alkaline conditions is shown, and remember that the fuel will react with hydroxide ions as it is under alkaline conditions. The answer is on the next slide. Now don't worry if you're struggling with these, they are really difficult and practice during class time will help. So on to the final section. This bit is straightforward as most of it is just recall. Firstly, you need to be able to state the advantages of fuel cell vehicles over conventional petrol or diesel powered vehicles. These are detailed in the table. The main advantages being that only water is produced and these engines have a much greater efficiency. However, the practicalities of making, storing and transporting a highly flammable gas mean that there are quite a number of significant disadvantages. We'll come back to the final disadvantage regarding the lifespan of the absorber and adsorber shortly. As the storage of hydrogen fuel cells is such a big issue, there are a number of different ways that this may happen. Again, you just need to be able to recall these. So one possibility is a liquid, whether that is at low temperatures or under pressure. The second and third options are related. Either the hydrogen gas is stored on an adsorber, so some kind of solid such as lithium nitride with a large surface area that can make temporary bonds with the hydrogen, or alternatively a solid that absorbs the hydrogen and it is stored within the solid. You just need to recall these 2 options. Further details on actual names of solids or details on how this works in practice is not needed. This idea, however, has limitations due to the fact that these solids may need to be frequently replaced and have a limited lifespan. Finally, you need to consider the limitations of hydrogen fuel cells and discuss their long-term viability. Despite the obvious advantages, the issues surrounding hydrogen storage and transport are real issues. As a result, an increased focus has shifted to hydrogen-rich fuels such as methanol and methanoic acid, which are liquid under standard conditions. They are also much less flammable. They do, however, produce carbon dioxide when they undergo combustion. But depending on their source, they could be considered as carbon-neutral fuels. So that's the end of the short topic on electrode potentials and fuel cells. You need to complete your booklet and have a go at the past exam questions on the topic.